Hello, Namaskar. Linear programming solution through graphic method. And now we are going to discuss a case where there is a situation of redundancy. A redundant constraint is one that does not affect feasible solution region. That means out of these four constraints, at least one is that kind of constraint that does not affect feasible solution region. That means there is no difference if that particular constraint or constraints are there as a part of problem or not. But at present we don't know which out of these four can be the redundant constraint. That we shall come to know only after drawing the graph. Yeah. In long term, by experience, by solving so many problems, you can be able to judge a redundant constraint only on reading the problem. But as we know that for you people, this is just beginning. So let's first solve the problem through graph, and at the end of the solution, we shall come to know which constraint is the redundant one. And according to the procedure accepted by us, first simplification, and in simplification first segregation of all constraints into equality and inequality. 5x1 plus 4x2 equals to 200, and the points available to draw the straight line of this equation are: if x1 is 0, then 200 divided by 4, so x2 will be 50. If x2 is 0, then 5x1 equals to 200, so x1 is 40. 5x1 plus 4x2 less than 200. If x1 takes value 0, then 4x2 will be equal to 200, and hence x2 will be less than 50. If x2 takes value 0, then 5x1 will be less than 200, so x1 less than 40 will be there. Second constraint, 3x1 plus 5x2 less than or equal to 150, and equation will be 3x1 plus 5x2 equals to 150, and that will give us the two necessary points to draw the straight line. If x1 is 0, then 5x2 equals to 150, so x2 30. If x2 is 0, 3x1 equals to 150, so x1 will be 50. Inequality will be 3x1 plus 5x2 less than 150. And if x1 takes value 0, then 5x2 will be less than 150, and hence x2 less than 30. If x2 takes value 0, then 3x1 will be less than 150, and hence x1 less than 50. In case of third constraint, 5x1 plus 4x2 equals to 100 will be the equation that will give us the two required points to draw the straight line of the equation. Yes. If x1 is 0, then 4x2 equals to 100, that means x2 25. If x2 is 0, then 5x1 equals to 100, so x1 20. Inequality will be 5x1 plus 4x2 greater than 100. Yes? Okay, if x1 takes value 0, then 4x2 greater than 100 will be there, and hence x2 greater than 25. If x2 takes value 0, then 5x1 will be greater than 100. That means x1 greater than 20. Okay, the last one. 8x1 plus 4x2 equals to 80 will be the equation, and the 2 points to draw the straight line of that equation will be: if x1 takes value 0, then 4x2 equals to 80, and x2 equals to 20 will be there, And if x2 takes value 0, then 8x1 equals to 80, so x1 will be 10. If inequality part is taken, 8x1 plus 4x2 greater than 80. If x1 takes value 0, then 4x2 will be greater than 80 and hence x2 greater than 20. Yes, if x2 takes value 0, then 8x1 greater than 80 will be there and hence x1 will be greater than 10. Okay. Now, this is the turn of drawing the graph of this linear programming problem. Yes, and scaling will be very suitable to us. This one is multiple of 5 and all other are multiples of 5 and 10. So we are going to take scale of 1 centimeter equals to 5 units. And in case of x1 axis we need to go up to 50, and in case of x2 axis also we need to go up to 50. So it is advisable to take scale of 1 centimeter equals to 5 units on both the axes. Yes. I am not going to remove the constraints because ultimately we want to know about the redundant constraint. So I am keeping the constraints as they are on board. Yes, as usual, I will be able to draw only the sketch of the graph of this LPP. You please draw the graph with utmost care on the graph paper. Yeah, some odd points can be there, so accuracy is necessary. Okay. We need 10, 1, 2, 3, 4, 5, 6, 7, 8, 9 and 10. 5, 10, 15, 20, 25, 30, 35, 40, 45 and 50. And in the same way on x2 axis, five, 10, 15, 20, 25, 30, 35, 40, 45 and 50. Okay. Now the first constraint, and in the first constraint the points are x1 40 and x2 50. x1 40 and x2 50, and we need to draw a line passing through both these points. Yes, that will be something like this, and this is 5x1 plus 4x2 equals to 200. Okay, and the less than sign is there, so x1 less than 40, that means towards 0, x2 less than 50, that will also be towards 0. Second is 3x1 plus 5x2 less than or equal to 150, and the equality part, x1 is now 50 and x2 30. x1 plus 5x2 equals to 150 is the equation of this line, and again less than, so x1 less than 50, x2 less than 30, that means towards 0. Okay, the third is 5x1 plus 4x2 greater than or equal to 100. 5x1 plus 4x2 equals to 100 is the equation. Points are x1 20 and x2 25. Yeah, x1 20 and x2 25. Okay. Yes, let's draw the line. Okay, this time it is greater than sign. So x1 is greater than 20. 20, 25, 30 and 35 and so on. Similarly, x2 is greater than 25. So outer side, opposite to 0 will be the shaded region or graph of the inequality part. And the last is 8x1 plus 4x2 greater than or equal to 80. And points on the basis of equality are x1 10 and x2 20. Yeah. Those, okay, first let me write the equation. 5x1 plus 4x2 equals to 100, and this is 8x1 plus 4x2 equals to 80. Again the sign is greater than, x1 greater than 10 outer side or opposite to 0, and x2 greater than 20 outer side and opposite to 0. Those from you who are alert can understand that any one of these two will be ultimately the redundant constraint, because the shaded region of both these constraints go opposite to 0, and the shaded region of both these constraints is towards 0. So somewhere here is the common region. If this is the common region, any one of these two should be there, and we are going to select. This is x1 greater than or equal to 0, this is x2 greater than or equal to 0, and here also in this way, in this way, and this is out of the common region. We can say that. So we prefer to draw or to select this region as the common region of most of the constraints of this LPP, because we don't need to include this, but I am going to shade this. Okay. Now it is upon us whether to consider this constraint or this constraint. You people can consider both of these and evaluate the objective function, but it is advisable to consider this part only. It is not compulsory. When I was a student, I know that before so many years this problem was also in our school textbook. At the time of learning, at the time of practicing, we were habituated to draw all the lines, to select all the possible area and to evaluate the objective function. Let's go for evaluation of the objective function. Corner point, coordinates, and value of z equals to 300 x1 plus 400 x2. But before that we need to write all the points. Okay. Now let's take the corner points. Which are the corner points? Say this is A. At A 20 and 0. This one is B. At B it is 0 and 25. This one is C. At C it is 0 and 30. This one is D. And at D I need to check it on the graph sheet. And this is odd value 31 and 11. Yes, this is somewhat strange. Please refer to your graph book Draw the graph carefully and see this point, rather these two lines don't intersect each other at any exact value. So I have in my graph book 31 and 11. You please check in your graph book. And the last point E, and that is 40 and 0. It's very clear. Now let's substitute all this in Z function. I am ignoring these 2 points. I am going to discuss them later on. But first of all, let's go with these points 20 and 0. 300 into 20 plus 400 into 0, that is 6000 plus 0 equals to 6000. Point B, 0 and 25, 300 into 0, 400 into 25, that means 0 plus 10,000 equals to 10,000. Point C, 0 and 30, that means 300 into 0 plus 400 into 30, so it is 0 plus 12,000, it's 12,000. Then D, 31 and 11, 300 into 31 plus 400 into 11, that is 9,300 plus 4,400, it's 13,700. E, 40 and 0, 300 into 40 plus 400 into 0, so it's 12,000 plus 0, it's 12,000. On the basis of this analysis, we can say that according to the maximization objective, the objective function takes maximum possible value 13,700 at point D. The coordinates are 31 and 11. That means x equals to 31, x1 equals to 31, x2 equals to 11 becomes the optimal solution to this linear programming problem, and the maximum value of the objective function comes to 13,700. Okay, that will be the conclusion. Now let's take the effect of these two corner points. If we include this constraint as a part of feasible region, and instead of these two corner points, we take these two corner points. Let's just check. If A is 10 and 0, might well, instead of this, if we take these this constraint as a part of our feasible region, what happens? So I use the sign A itself, but to differentiate it from the original A, I am using the asterisk mark, and this will be 10 and 0. So it will be 300 into 10 plus 400 into 0, so it will be 3000. Yes, and this will become B. Again, to differentiate it with our original B, I am using the sign of asterisk, and that will be 0 and 20. So it will be 300 into 0 plus 400 into 20, and that will be 8000. So even if we consider this constraint as part of feasible region, there will be no change in the optimal solution of the LPP. So now it is upon us, either of these two can be treated as the redundant constraint. Since this is actually on the outer side of, say, the common region of all the constraints, I personally prefer to consider this constraint as the redundant constraint. But it is not compulsory. Any one of us can treat this constraint as the redundant constraint. But the ultimate thing is, a redundant constraint is one that does not affect feasible solution region. If we consider this constraint as a part of feasible region, then this automatically becomes a redundant constraint. If we consider this constraint as part of feasible region. As we have done it, this becomes the redundant constraint. So, on the basis of this graph, it should be, I hope it is clear for you people that a redundant constraint is one that does not affect feasible solution region. That's it. Thank you very much.